Hello everyone, this is my solutions for the decision tree examples, which is chapter 11 from the operations research book with from Taha. And I included two examples, and now I'm gonna show you their solutions. So here is the first example. I'm gonna show you the decision tree and how to solve it. So if we start reading through the question, we see that the first thing that we as the management need to make a decision for is whether to have a plant burning or to postpone it, which we write here. Like it is pointed in the notes, we have a decision making. That's why we put 1 in a square, because this is a decision knot, and the two decisions are either to plan a burning or to postpone one. And as we can see, if it's postponed, we're gonna lose $300, which would take us on this way of the tree. So we're gonna lose, that's why it's a minus $300. Or if we plan burning, we get to a node, and this node is a chance node. That's why it's in a circle. So we have a chance of good weather, which is 50% or 0.5, or a bad weather, which is also 0.5. And in the case of a bad weather, we're gonna lose $1,200. In the case of good weather, we gonna continue with the burning, and that's gonna cost us $3,200. And then we have another chance, not here, which is in a circle because it's a chance, and with a number 3. And the two options are to have a successful burning with a probability of 0.6, and this way we'll make $6,000, or we can have a marginal burning with a chance of 0.4, and this way we will gain $3,000. So this is pretty much the tree. Once I'm done with the solution, I'll show you how to do the tree in LaTeX, and that's one of the reasons I chose this chapter, just to practice the text picture functions and play around with them. So let's go to the solution. So we can work backwards from the tree. Start from node 3, go to node 2, and get to node 1, and find out if we need to postpone or plan the burning, what is the best solution. So the expected value right here for good weather to come over here at node 3, we have we can make $6,000 with probability 0.6, or $3,000 with probability 0.4. So the expected value for having good weather would be 6,000 times 0.6 plus 3,000.04, which is $48,000. However, we need to pay $3,200 for the burning cost. So the expected value for that branch from 2 going into 3 would be 4,800 minus 3,200, which gives us 1,600. So if we, right now we're here for the planned burning, we have the two options, good weather or bad weather. So we do the same thing. Our expected cost, if we have good weather, is 1,600. We multiply it by the probability of having good weather, which is 0.5, and then we add how much money we're gonna lose in case of bad weather, which is 1200 multiplied by the probability for bad weather, which is 0.5, and the result is 200. So expected value of planned burning is 200, and then the expected value of postponed burning was in 300. So comparing 200 and negative 300, we'll always make money if we plan a burn-in, but if we postpone it, we always lose money. Therefore, it only makes sense that we continue with the planned burn-in. And this is the solution for the first question. Let's look at the file. So to start at the beginning, to build the decision tree, we need to use the package ticks. And also, I will show you here how this is just how to create the tree nodes, the root, the environment. And I just found this online, copy and pasted and modified it for my needs. So if you want to just pause right here and copy this into your LaTeX file or look it up later on, we create the different type of nodes. So like I said, we do a square one for decision or a rectangle. This is the dimensions, and you can change color or you can change the shape. I'm gonna show you this in a little bit. This is how the chance looks like. So for chance in the Tahoe book, it was a circle, so I kept the same notation, and the one that is called a line, there is just nothing, it's just empty, which would correspond to like the final leaf, like right here, here, and here. Another thing that we need to show is that our tree is going from left to right, so that's why we have the right, and our levels, so this would be 1, 2, and 3, corresponding to our levels 1, 2, and 3, and then we give the distance between its siblings and the level distance. So siblings in this case would be this one and this one are siblings just because they have the same parent. This and this is siblings together, and this is the parent, and those two are siblings with this is their parent. And let me just show you, like if I change the distance, and the distance is how long the branch is. And you can play with the numbers. I just decided on those numbers, so my labels would fit. You can also choose if you want them on the top or the bottom, and I'll show you when we go to the particular tree how to do that. And let me just show you how we can change the distance. So for example, the siblings on the first level, we only have one, those are those two siblings on the first level. So we can make the distance between them much smaller. So let's say distance of 3, and I will recompile just to show you how the distance between them changed. The level distance, like I said, is that distance over here. I can change that to say 2.5. And then you can just play with the numbers and see what works best for, so you see how they became smaller. But later, as you see here on my next graph, they also change, so you'll need to pay attention to that. So let me just put them back to what they were. And I'll just recompile. So now we can see exactly how they work. And this is the code for creating that particular tree. So we begin the text picture and we start with the first node. And another thing that I have noticed, once you put all the children, so you write down a child, you know, write down node and what type of node it is, and then what is it gonna be the name of the node. So for example, the name here is -300. Then you create an edge from the parent, so this is the edge, and then you can create a label, and also you can put the label below or above. So in this case, the label right here is below. I can change it to be above, and that's just a personal preference. So it will change and go on the top. Or you can have both, which is the case right over here. So if you wanna just pause for a second and look, this would be the code for the tree. And I will go now to the second example. So this is our question 2. So we know that we have a disease that you can be tested for, and there is a chance that you have it or not. So we start with a chance node, which is marked with 1 in a circle. And the chances are that you have the disease is 0.1. And the chance that you do not have the disease is 0.9. So those two branches split up to, if you have the disease, it says that 20% of the tests will give you negative results, which comes over here. So you have the disease, but you have a negative test, or you have a positive test, which is with probability 1 minus 0.2, which gives us a probability of 0.8 to have the disease, and given that you had a positive test. So on the bottom branch, if you do not have the disease, again, it says that 20% of the tests give false positive test, which we marked over here, false positive. And you don't have the disease, but you got a positive test, and tests that are correct that you do not have the disease have probability of 0.8. So how I solved this, I let a positive test to be a plus, negative test to be a minus. If you have the disease, Y for yes, or you don't have it, and for not. And then we can write a statement of probabilities as what is the probability given that you had the disease, you got a positive test, is 0.8, which would be that branch over here. The second one says you got a positive test, but you do not have the disease, which is right over here. You have a negative test, but you have the disease, would be that branch. And you do not have the disease and you got a negative test, is this branch here. So we can write this in the probability table right here. So I just got these values and plug them into the table. And now we need to compute the joint probabilities. So how we do that? If you follow the steps, we have that the given probabilities to have the disease is 0.1 and not to have it is 0.9. So we are just multiplying each row by the respective probabilities. So for yes, right here, we're going to multiply by 0.1. For no, we're going to multiply this row by 0.9, and we will have our new table. So these probabilities all need to sum up to 1, which I have showed over here. And the absolute probabilities for have a positive test and a negative test we're gonna get by summing up the column. So the probability to have a positive test is 0.08 plus 0.18, which is 0.28, or the probability to have a negative test, we can subtract that number from 1 or just sum up the column. And now to determine the desired Bayesian or posterior probabilities, we divide each column by the respected value. So to find the probability that you have the disease, given that your test was positive, we need to divide the probability that you have the disease and it's positive by the probability that it is positive, which would give us 31%. So that is a much bigger probability than the given probability that was of 10% that we started with. So again, if you want to look at my code, it is right here. So we started with a change node just because it's a chance that you have the probability or not. It's not a decision. And it has 2 children, 3 and 2. And I don't know if I've mentioned that before, but the one that is drawn on the bottom usually comes first. So right here, 3 is the child or node that is on the bottom, and it always comes first when you list them. And again, when you list the child of the child or the grandchild, which is no disease given with a negative test, it always comes, the first one always comes on the bottom. So this would be the code. Let me just zoom out a little bit for the second 3. And you can see how to do it. Again, this is another way to see how to do the decision tree. We could have used probabilities, but this is just a nice way to see all the different possibilities that we have. Again, thank you for watching, and have a nice day.